Hello everyone, my name is Goran Žužić and I'm going to be talking today about hop-constrained Oblivious routings. This is joint work with Moxon Ghaffari and Bernard Hoyper, and it is set off here in STOC 2021. So the first thing we're going to do, I'm going to motivate the problem for you. So imagine the following. You are given a graph G that is undirected and unweighted, and here you have on this graph G a bunch of sourcing demands. So you can see you have like S1 and T1, then you have S2 and T2, and you have S3 and T3, and you want to choose paths between them. So you might want to choose like this path between S1 and T1, the blue one, and the green one. Okay, you chose those paths. How do you want to choose them? You want to choose them to minimize the make span. All right, what does that mean? Imagine that there is like a car at the beginning of each path, and now the question is, when is the time until all the cars reach the destinations? And the model here is, in one round, so one time step, one road passes exactly one car. Okay, what happens? Let's see a simulation of this. So cars go, and at time 11, everyone is done. So let's do this again. So as you can see, like the red car just zoomed through the destination. It had a lot of time, and that's kind of what dominating the time because it has a very long path to go through. However, I would like you to pay attention on the green and the blue car. Now, in the first time step, they both go to the same city, and now in time 2, they want to go to the same road at the same time. However, this road only can support one car going through it, so only the blue car passes and the green car does not. And at the end of the day, they both finish, and this is it. So the point here that I wanted to put your attention to is that, if many cars want to pass through one road, it's going to take a lot of time. Okay, so you want to choose the paths that minimize the make span. We just explained what make span is. That's like time until everyone reaches their destination. And finally, and very importantly, the paths are chosen obliviously. Okay, what does it mean? Well, you can think about it in the following way. So each driver has an offline mobile application navigation app that produces a path to him. So like him or her enters like a path, enters the starting point and the destination point of its path, and the offline navigation app, tells the driver where to go. Okay. Now, what does it mean that it's offline? Well, the point that I want to emphasize here is that the offline mobile navigation app does not have information about where the other drivers wants to go, or who, or even how many drivers wants to drive that day. The navigation app, it only has the source and the sink of that one driver that is querying the app, and it needs to be oblivious with respect to everyone else. It needs to produce a path that has nothing to do with the other drivers, and it needs to still produce a good path that produces a good make span. Okay, so formally, what does this mean? I'm going to define you the notion of oblivious routings because this kind of oblivious choosing the path is very often called an oblivious routing. Okay, so when you're given a graph G, an oblivious routing R is a collection of V-squared distributions R of UV. So basically for every node UV, you have a distribution of paths R UV between U and V. Okay, so basically, so every two nodes, you have a distribution of paths between those two nodes. That's an oblivious routing. Given this oblivious routing, how do the drivers actually pick the path? Well, each driver has a source and a sink, and then the driver samples a random path from the distribution R of ST, from with that source and that sink, and drives along it. And why is this oblivious? Well, you can see, I'm telling you, all drivers want to sample from the same R. So you have one distribution, so there is only one offline navigation app. The navigation app has only one distribution that it knows, and you want it always to sample that same distribution. So, like if driver I chooses, queries between SA and TI, that has nothing to do with another driver querying between SJ and TJ, or does the other driver even exist? The SI-TI result is independent of the other drivers. Okay, hopefully I drilled this in. And now let's pose the question that you're going to study here. So given a graph G, does there exist a single oblivious routing R of G whose make span is always polynomial competitive with the offline optimum for all possible demands? By demand, I mean all possible set of drivers, or like sourcing destinations of all drivers. Okay, and by O tilde 1, I'm typically gonna mean polylog in this talk. Like, I'm always gonna mean polylog in this talk. All right, so what's the answer to this? Does it exist? Well, depends on how you interpret it. If you interpret it in the most straightforward, naive way, the answer is actually no. And there is a very, very simple reason why this is impossible. So I claim that no single oblivious routing suffices for minimizing make span. And this was actually noticed quite a while ago by the pioneer of oblivious routing, Recke, in his thesis in 2003. Okay, so the simple example is the following. You take a graph, and now you connect 2 points S and T with one path with one hop. So it has like low capacity path and low length. And then you also connect it with many, many, many paths of large hop. So basically you have a high capacity highway, but that's also quite long. So now, why does not exist any oblivious routing? Well, if there is only one driver, one demand, what do? You just send from S to T, obviously. You send it along the short paths, and you get a make span of 1. It just needs like one step. On the other hand, if there are M drivers, well, then you need to send them along the long paths. Since there are M paths, each driver goes along its own one, and all of them actually finish in square root M hops. So, because you can see that this is not oblivious. If there is one driver, you need to send it along the short path, and if there is many drivers, you need to send it along the long paths. But the app has no idea what are the other drivers, know how many there are, know anything like that. So you cannot be perfectly oblivious. So the answer is no, if you interpreted it this way. But I would like to say you can get the very best next thing. So yeah, you cannot be perfectly oblivious because it's a very strict constraint, but this is kind of what you can get. So let me parse this for you. So given a graph G and an optimal solution, opt, there exists a single oblivious routing R that depends on G and opt, whose make span is O tilde of opt for all demands whose offline make span is theta tilde of opt. Okay, so what does this mean? Basically, guess the solution opt, guess what the optimal make span is. And now there is a single routing that works like near optimally for all demands whose offline make span is opt. All right. So this one routing will be near optimal for all the demands where the centralized routing that knows all of them in advance is the best solution is exactly opt, is like around opt. Okay, so does this even help us? I claim, yeah, absolutely. You can always guess and double. So what you do, you guess opt, you query the oblivious routing, every driver samples a path from R, G, opt, and drives along it. If it succeeds, then great, you're done. And no, and if it does not succeed, well, like if you don't reach the destination within opt time, you drive back and you double opt, and that's it. So this will only lose you like an insignificant like log factor, which we ignore in this talk. So basically, this result kind of that we do basically get a way to minimize make span, an oblivious routing that can be used to minimize make span in many, many, many interesting models. Even in highly decentralized model, you can use tactics like this, and you can get a routing that is like near optimal with respect to make span. Okay, so that's that with the introduction. So let me talk a little bit more about the background of this problem. So one thing that I would like to show you is that make span is more or less, you can think about it as congestion plus dilation minimization. Okay, so what is dilation? Well, the dilation H is the hop length of the longest chosen path. So if you can remember here, when you have like a path of length 11, so if you can see here, if you have a path of length 11, the dilation of this path is 11, and the dilation of like a set of paths is just the maximum dilation of any path. Fine. Similarly, let's define the congestion. So when you choose a bunch of paths, the congestion C is the maximum number of paths passing through a single edge. So in this picture here, we have, it's not see. Can you see this? There are like 4 paths going through this like one black edge. So the congestion of the edge is 4, and the congestion of a set of demands of a set of paths is just the maximum congestion over all edges. So, okay, why do we even define this? What can we say about the makespan opt, so the minimum number of rounds until all the cars can reach the destination? Clearly, opt is bigger than the duration. That's kind of the example that we saw in the beginning. There was one very long path, and because this one car needs to go through this path, and even this one car in isolation is h hops, opt is definitely bigger than h, well, clearly. Similarly, opt is bigger than the congestion C because, well, if there are like 4 cars going through this edge, you need at least 4 times until they just pass through this edge. But okay, so this is a lower bound on opt. However, there is an upper bound that says it's at most C plus H. So, and this is a result, a classic result by Leighton, Meggs, and Rao. Now, in the centralized model, Leighton, Meggs, and Rao say well, you can actually lose only constants. You can do C plus H up to constants. But, in these distributed models where you have drivers that know each other and you cannot really schedule them in a centralized way, well, you can lose like a log factor by different techniques. So like the most famous one being the random delay technique. But I'm not going to go into this, but the thing that I want you to remember is minimizing the makespan is the same as minimizing the congestion plus the duration, up to log factors and you don't even need to lose the logs in every model. So just remember, minimizing makespan is same as minimizing congestion plus duration. It's like a joint minimization of congestion isolation. Okay. Now let me tell you a little bit about prior work. So Oblivious makespan minimization is also called congestion plus dilation or C plus D minimization. Has been studied for quite a while. The most famous example is the so-called Valiant trick that asks you, can you do Oblivious routing on hypercubes? And the answer is yes, you can do Oblivious routing on hypercubes, and you can get O of log n competitive makespan minimizing Oblivious routing. And this is a very famous trick. I'm sure many of you know it. And it tells the following. Well, every driver that wants to go from S to T just picks a uniformly random intermediate node M. So choose a uniformly random intermediate vertex M. And now you greedy route from S to M, and then you greedy route from M to T. Greedy route, I won't go into it, but it's like the most natural routing that you can think of, most natural deterministic routing that you can think of. So yeah, go to an intermediate node and now go to the final destination. And the claim is this is going to be log n competitive with the optimal solution, regardless of what the other drivers are doing, nor how many there are and anything else. This is going to make spend minimizing. Okay, so this is a very cool and well-known trick. The same trick kind of works also, let's say, in expanders because you can kind of embed expanders in hypercubes. And there also was significant work that showed that you can do something similar in grids, in fat trees, in meshes, scaly graphs, and so on. So the thing that I want to impart in you is that there was actually a lot of work done in this, done on this kind of Oblivious makespan minimization setting. Moreover, this Oblivious makespan minimization was listed as one of the 8 open problems in distributed computing by Astnes et al. In 2006. So they say another important open problem is to find the classes of networks in which Oblivious routing gives congestion plus dilation close to the offline optimum. Such a result has immediate consequences in packet scheduling algorithms. All right, I mean, by packet scheduling, we mean kind of, well, this driving or makespan minimization, that's kind of the same thing. I said drivers, but this, you can think about it, the more classical example is, I guess, minimizing the time until all the packets reach their destinations. But the point here is that this is an open problem that people have been looking at. However, they seem to have missed the result for all graphs, and they seem to have posed the question, well, what are find the classes of networks in which you can find oblivious routings. They didn't tell us, well, is there an oblivious routing for all graphs in which you can do this? And it's not super clear why, because this result that we get seems to have been missed. I mean, I would imagine it was probably due to the impossibilities result that I was shown before, and that basically all of these papers that work in this model kind of cite in the beginning, in the introduction, they say, well, we cannot really get the best thing, so let's consider special graphs, like the expanders or fat trees or grids or whatever. But it's still strange, and maybe another reason is, the result is fairly technical involved, and the techniques haven't been developed before. So this might be like a first time until we can actually tackle this problem in a way. Interestingly, the result was missed, and it's not super clear why. But, hopefully we can rectify this. Okay, so on the other side of prior work, there have also been considered other quality measures that are not, Make-Span. Most importantly and most well known, the Oblivious routing that started this entire field is the congestion minimization Oblivious routing introduced by Recke, and actually optimized by Recke in 2008 to its final log n factor that says the following. For every graph G, there is a single Oblivious routing where the congestion of the paths obliviously chosen are log n competitive with the offline optimum with respect to all possible demands. So basically, whatever SITI demands you have, sample random paths with respect to this oblivious routing, and you're going to be, the congestion of this path is going to be log n competitive with the offline optimum. So it's not make-span, it's congestion. And you can think about it, well, make-span is congestion plus dilation. This is just like one of those terms. And this, this has been done. This only takes the edge congestion into account, doesn't take the dilation, so it's a little bit different. And actually, there was a lot of work that followed this result and also line of results. So, for instance, I'm just gonna sample a few of them. Gupta et al. Show an log squared competitive oblivious routing. If you look at a different quality measure, so not really the maximum congestion as before, but more like some sum of monotone subadditive functions of the congestion of the edges. All right, and also Engert and Recke 2009 give like a little bit different result. It gives a log n competitive oblivious routing when you look at the LP norm of all the congestions of all the edges. So the results are a little bit more general that I give them credit here, but this is kind of their flavor that I want to impart on you. Okay, so now let me tell you a little bit about more results. Let me define the results that we get a little bit more formally, because the previous one was quite an informal definition. So, as you remember, there is this impossibility result that you cannot directly optimize the make-span. What we do actually is we fix H, the dilation, and then we optimize the congestion with respect to this dilation H. So, imagine what is the best congestion? The offline optimum is, you can think of the offline optimum as the best congestion that you can get when using paths of at most H hops. So now you want to be competitive with this H hop congestion. So let's define our H hop oblivious routing, our notion of H hop oblivious routing. So given a graph G, and also H actually, an H hop oblivious routing, R of GH. So that gives you, that for every two vertices you get a distribution over paths between those two vertices. We say that this oblivious routing has hop stretch beta if all the distributions R of UV are supported over paths of at most H times beta hops. So even though H is the parameter, in the oblivious routing you are allowed to do a little bit more, like beta more, hop stretch more. And hop stretch you want to be a polylog, obviously, at the end of the day. And also we say the oblivious routing has congestion approximation alpha if for all demands SITI, so all possible sets of drivers going from SI to TI, the following holds. Each driver samples a path PI from R of SITI. So each driver samples a path from the distribution. And now the expected congestion, expected because this is our random path, the expected congestion is alpha competitive with the optimal H-hop congestion. By H-hop congestion, I mean the best congestion you can get using paths with much H-hops. So kind of you can see here is, you can actually get this. When you define it in this way, you can kind of get it. For every graph G and every H, there exists an H-hop oblivious routing that has a polylog hop stretch and a polylog congestion approximation. And in red, I just put anything that has to do with, I just highlighted the, in red H, I just highlighted the dilation, the hop bound or the dilation bound. Good. And I guess one thing to point out is here, we kind of have some kind of a bi-criteria optimization problem going on here. So if you're comparing yourself an H-hop path and dilations with H-hops, you're allowing a little bit more hops to use, and you're allowing yourself a little bit more congestion. And also, you can notice that the dependence on H is very, very weak. It's only like in the log factor. So even if you take H to the n, or square root n or anything like this, it's still going to be a polylog. Okay. Now, good. So let's continue on. Now, this is a short talk, so I'm not going to give you many technical ideas, but I'm going to just illustrate a few of them. Okay. So let me tell you why all the previous approaches kind of failed. All the previous approaches were dependent on so-called tree-based routing. So all of the approaches that I know of, and I'm pretty sure all of them that were used, were kind of relying on tree-based routings. So what is a tree-based routing? Well, there is a collection of trees T1 to Tk, and how do you route, what is the oblivious routing? Well, every demand from S to T just picks a random tree and then routes along it. So there are these T trees, and then you pick a random one, this one for instance, and then you just route along from S to T, however the tree tells you where to go. Now, yeah, all previously considered constructions of oblivious routings were tree-based, fine, but the problem is there is no way to get a polylog hop stretch and a polylog congestion approximation oblivious routing for the make span or for the dilation plus congestion if you're using tree-based routing. Like, you cannot do it. So you needed to have a very new notion of how you actually route, that is not tree-based, or also known as linear routings. So the big idea here is that we don't use tree-based routing, but partial tree-based routings. So what's a partial tree? Well, it's a tree that doesn't embed all the nodes, but just embeds a subset of the nodes. And actually, like different trees embed different subsets. So in the picture here, you can imagine like that this striped nodes are not embedded. Well, like you cannot really if you sample this tree, well, if you want to go somewhere between this one, then you're kind of out of luck. Not sure what you do. We'll talk about it a bit later. But if you want to go through like these gray nodes, that's fine. Between gray nodes, that's fine. You can always do that. Yeah. So the idea is that you use these partial trees. And now, I claim that the partial tree distribution can support so-called rounding with errors. Okay, so what does this mean? For any Garvey tree and any hop constraint H, there is a distribution, there is a single distribution of partial tree embeddings with hop stretch polylog, such that, for any demand, you take, you drop 50% of it, and the things that you do not drop can be routed with polylog congestion approximation. All right, okay, fine. So basically, yeah, just to say it one more time, basically you take any demand, there is a single routing such that for every demand it supports half of it. You can think of, so for instance, and now, what happens is, because you're using partial trees, let's say that you want to go between two nodes that are not in the tree, that are not embedded, two nodes that are dropped, or maybe even one node that is dropped. Well, clearly this is an error. You need to drop this demand. So that's how, you can actually route in partial trees. Well, some of the demands are not, able to be routed. What can you do? However, you start to this routing with errors, but then you can use some error correcting scheme. And you can actually fully eliminate errors with a complicated schemes that I won't describe here because of sort of out of time. But at the end of the day, you have this like very simple routing structure. So for every ST, there is a single distribution. There are no errors, and in expectation, you're perfectly fine. So you can error correct in a very meaningful way. Okay. So now let's end up with the conclusion. I'm going to talk about connection to other areas. So this is a kind of a new result that hasn't been attained before, and it seems to be opening the path for results in different areas of theoretical computer science. Well, the one that's personally very close to me is the universally optimal distributed algorithm question, which is actually the original motivation why we even started to look at this. So the problem is you're given a distributed network, and you want to solve the distributed min and spanning tree, distributed single source shortest path, distributed min cut, and so on. Now your goal is to find a single algorithm that is as fast as possible for a given network G up to polylogs. So basically, if the best possible algorithm that this network works in, I don't know, T rounds, then I want you to give me an algorithm that works in T polylog rounds. So, that is like polylog close to the optimal. And we kind of get this. So in a paper by Hoyper, White, and me, in STOC 21, we get that if the network G is known in advance, but you don't see the input, so the MST, you know the network, but you don't see the edge costs, then there is a single algorithm that is as fast as possible on all networks. So there is a single algorithm, you feed the network in advance, but then it can answer any possible MST cost or single source shortest path cost or minker cost in like optimal time. In optimal time. And now the open question is kind of remaining. Can you remove this if the network G is known in advance? And for this, all you need to do is construct efficient hop-constrained oblivious routings. So if you can construct efficient hop-constrained oblivious routings, as in like imagine near linear time in the centralized model, but in the distributed model it's like polylog time. Let's imagine something like that. Then a single distributed algorithm, you would get a single distributed algorithm that is optimal on all networks simultaneously, which seems amazing, and it's not even clear that such a thing would even exist. But we proved that you can get this. And the connection here, why this is even connected, is that, well, we show in this paper that many problems in these distributed models are equivalent up to polylogs to simple pairwise communication problems, well, that you can solve via this oblivious routing methods. Okay, but there is also a bigger picture here. Like the bigger picture is like this question of optimizing makespan fits within this bi-criteria optimization of both congestion and dilation simultaneously. Well, this comprises many questions that were studied along, many papers. They're very interesting, but also very hard. And there haven't been like one technique that would like solve them. There are like many techniques, and they were generally solved in that correct way. It's very cross-disciplinary research. It even spans like network coding and information theory and approximation algorithms and this like routing algorithms and load balancing and so on. And there is much more research and understanding that needs to be built in order to like grow this area. But we do get a few results of this kind. For instance, one thing that we get is like tree embeddings that give you the tree embeddings for hop-constrained network design. This is another paper by Hoyper, Hershkovich, and me in STOC 21. And we give like a general purpose tree embedding that is able to deal with many problems with hop constraints. So like a hop-constrained minimum spanning tree or a hop-constrained Steiner tree, hop-constrained Steiner forest, hop-constrained group Steiner tree, and so on. Using this like very general purpose tree embedding technique, you can get bi-criteria guarantees for them. And another quite a different example is like the network holding gap for makespan minimization. This is a paper in Fox 20 appeared by me, Hoyper, and David White. And the question there is, how much does network holding help versus routing in communication if you are worried about makespan minimization or dilation plus congestion minimization? using, well, relatively similar techniques than we use in this paper, we show that actually coding that cannot help too much. Well, it can help, you know, by a polylog, but it also cannot help more than a polylog. So this is it. And there are many, many different results and the directions that one can study here. This is like very, very new, hot off the press. And perhaps your next application could use this, or can use the framework that you build in this paper, or the advancement in this conjecture plus dilation problems that we attain. Okay, so thank you all, and thanks for the attention, and this is it.